Hi everyone, so in today's video we're going to be looking at the HR part of unit 3, so the first row D block elements. So here we're going to be looking at the transition elements that owe their characteristic properties due to the incomplete D subshells that they have. Remember that when we fill in the electrons, we fill in the 4s shell first, then the 3d. So you find that the D subshell is partially filled. So for it to be completely filled, it should have 10 electrons. So as long as it's partially filled, it's called a transition element. So when we look for trends and discrepancies across the transition elements, they follow certain patterns of behavior, but zinc, chromium, and copper do not follow these patterns and are therefore considered anomalous in the first row D block. We'll be looking at these anomalous properties. So characteristics, the 5 main characteristics of transition metals that you should know is that they have variable oxidation state. For example, you could have Fe2 plus or Fe3 plus. It all depends on the element, but they have several oxidation states. They can form complex ions with ligands. So these are examples of complex ions. They form colored compounds. So here you have this compound which is pale pink and this compound which is green. They have catalytic properties. They act as catalysts. So iron in the Haber process, vanadium 5 oxide in the contact process. So either the element or the compounds of the element is going to be a good catalyst, and they have varying magnetic properties. So we're going to see all these properties for transition metals. So elements titanium to copper. So titanium to copper. So here you have a list of all the D block elements. So from titanium to copper, they are considered to be transition elements because these elements can form at least one stable ion with a partially filled D subshell, which means that the criteria for it to be classified as a transition element is that the ion, it should have at least one ion with a partially filled D subshell. But when we look at this criteria, scandium and zinc do not fall in, because if you look at scandium, if it would be forming scandium 2 plus or scandium plus, it would lose electron in the 4s subshell, which means that the D subshell will have one electron, but scandium 2 plus is unstable. So the ion that is formed by scandium is scandium 3 plus. So when scandium 3 plus is formed, it has no electron in the 4s or the 4d. So it's just the electronic configuration of AR. And if you look for at zinc is going to lose. So zinc forms Zn2 plus, and it just loses these 2 electrons in the 4s subshell. So then the D orbital, D subshell, is not partially filled. For it to be partially filled, you should have either D1, D2, 2, D9. These are partially filled D subshells. So scandium and zinc do not form stable ions with partially filled D subshells. Now, transition metals, they can form ions with variety of oxidation states. So as you can see in this table, you have the common oxidation state. This is available in the data booklet. So you will see all the common oxidation state. The unstable ones are not shown over here. And when ions are formed, the s electrons are lost first. Because the 4s subshell has less energy than the 3d subshell. So this is why electrons are lost from the 4s valence subshell before the 3d subshell. So all transition metals show oxidation state of +2. all of them, but for scandium can also form +2 compounds, but they are not stable. So here you see all of them form the 2+. Now for this question, let's write down the electronic configuration of these ions. Before you write the electronic configuration of ions, make sure you write the one for the atom first. So chromium is 26 electrons. Let's write for chromium first. And also it's asking you full electronic configuration, so I'm not going to use AR here. So 18 electrons, I have 18 electrons here, and 19, 20, I fill in the 4s first, and then I fill in the 3d. So then 4 electrons goes here. But remember that the 3d subshell is more stable when it's half filled. So then we'll have a slight adjustment. So 1 electron from the 4s moves into the 3d. So then I'll have 3d5, 4s1. And when I have Cr2+, that is going to be formed, I'll lose electron in the 4s subshell first, then in the 3d. So that means I'll have 3d4. So 1 lost here and 1 lost here. Now chromium 6+, I'm going to lose 1 here and 5 here. So it's going to be empty over here. So I'll just have the 18 electrons. Here you go. Make sure that whenever you have to write electronic configuration of ions, you always start with the atom first. So if we have to explain why chromium 6+ is more stable, if we look at chromium here, so it has the electrons filled in the 4s and the 3d subshell. If you have to form Cr6+, so then it would be losing all these 6 electrons. And when it loses these 6 electrons, the 3d and the 4s become empty. So an empty orbital is going to be stable, because then everything that is before is going to be completely filled. So why is it the most stable? So this is what's going to happen. It's going to lose 6 electrons from the 3d and the 4s subshells to form Cl6+. Hence the 3d and the 4s subshells are completely empty, as you can see here, and this is a stable electronic configuration because everything else inside is going to be completely filled. So given that the highest oxidation state of zinc is 2+, outline was why copper is considered as a transition element but not zinc. Now if you look at copper, so this is the electronic configuration of copper. So copper is going to form Cu2+. As it forms Cu2+, you are going to lose 2 electrons, so that's going to be 3d9. So 3d9, this is a partially filled d subshell. So hence copper is considered as a transition element because it has a partially filled d subshell. Here you go. Now if you look at zinc, so that's for zinc. So even if zinc would be forming Zn plus or Zn2+, so the question tells you that the highest oxidation state of zinc is 2+, so it could form Zn plus or Zn2+, let's say. So even if it's Zn plus or Zn2+, it would still lose electrons from the 4s subshell. So which means that no electrons are lost from the 3d subshell. So here you go. So if this was an IB question, if this question was for in the exam paper, you could actually answer it like this. There is no need to write a lot and not be able to explain what you really mean. Answering like this in the answer box given, that would also give you your mark, because you are showing the electronic configuration and you are saying it's very important to add an annotation to your answer where you're explaining why this is a transition element and this is not a transition element. Right. Now you have to know that the term oxidation states and oxidation number are actually not the same. Oxidation state is the charges, that's oxidation state, and oxidation number is the Roman numerals. Actually, for your level, you don't really need to know, need to specifically know, but it's good to use them appropriately. So when you're referring to charges, refer to oxidation states. So actually, oxidation state is the number of electrons that the atom is going to gain or lose. So this is why it has charges, but the oxidation number is going to be the charge on the central atom when it's surrounded by ligands. We're going to see that when we're going to look at coordination complexes. So when we're considering oxidation number, we're considering that bonds are totally ionic, but when we're looking at oxidation state, so it could be electrons gained, lost, it could be electrons shared as well. Okay, so just make sure that you use them appropriately, but you don't really need to know, you won't be asked what they are, but use them appropriately. So when it's the charges, it's oxidation state. When it's the Roman numerals, it's the oxidation number. So comparing ionization energies, so here you can see that for the first two ionization energy, they're fairly low, and then you have a jump over here. And for titanium, the first four, so 1, 2, 3, 4 is fairly low, and then you have a jump over here. So let's see. So these are the electronic configuration. You need to write the full electronic configuration, so no AR. I'm just writing that for explanation purposes. So here, if you look at calcium, when you're using the 2 electrons here, so the first 2 electrons from calcium, these are from the 4s and 4s again, and then the third electron, when it's being removed, this is being removed from the 3p here, that is inside. Here you go. So first 2 electrons here, the third electrons is from the 3p subshell. So definitely there's going to be a jump here. So here you have the explanation. So the first 2 electrons are removed from the 4s subshell over here, and then the third electron onwards are removed from the 3p subshell that is closer to the nucleus, hence requires more energy. This is why you have that jump over here. If you look at titanium, so there is 4 lower energies, and then you have that jump. So this is because the first 4 electrons are removed from the 4s and the 3d, and the 4s and the 3d are very close in energies, so this is why there is not a huge gap between them. So the first 4 electrons are removed from the 4s and the 3d that are close in energy, then the others are going to be removed from the inner 3p subshell. So this part has already been answered. Let's look at this one. So you have ionization energies of vanadium. So you have to state the sublevels from which each of these first 4 electrons are lost. So let's write the electronic configuration of vanadium. So the first electron is removed from the 4s. Second is from the 4s. The third one is going to be removed from the 3d, and the fourth as well from the 3d. And if you had a fifth one, the fifth one would also be removed from the 3d subshell. So this is why. So then at the sixth one, there's going to be the jump, because then the sixth electron is going to be removed from the inner 3p subshell. Why there's an increase in ionization energy from electron 3 to electron 5? So from electron 3 to electron 5, the electrons are being removed from the same subshell, from the 3d. But what is happening is that the charge on the ion is increasing. So electrons being removed from the same subshell but with increasing charge means that there's going to be more attraction, more electronic electrostatic attraction, and it's going to become harder to remove electron from that charged particle. So here you are. So electrons are removed from the same subshell, and as more electrons are removed, the positive charge on the ion increases, and it's going to hold the remaining electrons more tightly. So you're going to require more energy to remove electrons gradually. Okay, right, so that's it for the first part of this. There's one question here: explain why there is a large increase in ionization energy between electron 5 and electron 6. So electron 6, the electron is removed from the inner free p subshell. Okay, so you can write that down, and we're going to see magnetic properties in the next lesson. So thank you.